Hello, Stats 300, and this is Professor Gonzalez. And I would like to go over some problems on the assignment side of ALEKS, covering the problems that we have in section 9.3. Now, 9.3 is a section where we're doing the hypothesis testing, just like we did in 9.2, but there is one major difference, and we can see that on the formula sheet. Let's go down there. And the big difference here, now this right here is 9.2, and this is 9.3. Now you can see the big difference, the first big difference, I guess you can say, is on 9.2, we have this sigma, which is the population standard deviation. Whereas in 9.3, we don't have the population standard deviation, but we have something that's actually easier in real world, easier to get. And that is, if you have a sample, it's easier to get the sample, right? Because it's just from a smaller group, a sample of maybe 100 people. And from that sample, we can find the standard deviation from that sample. Okay, so 9.3 is performing a hypothesis test when the let's make sure we see this, when the population standard deviation is unknown. And if the population standard deviation is unknown, we can use the sample standard deviation. And that's the big difference between the two. And so what that means is because we have a sample standard deviation, and we talked about this in our confidence intervals, that there was a similar thing when we don't know the population standard deviation. We can use the sample standard deviation, which allows us to use these t distributions, right? T scores rather than z scores. Okay, so that puts us on a different test statistic, which is t. All right. So before we get started with that, they're asking us some sort of preliminary questions, trying to get us used to doing some of these problems before we do a full-blown hypothesis testing problem. They're asking us, can you just find out what these p-values are? And we did p-values in the last problem, but let's do it again. It's a little bit different. And just to be honest with you, when I ask for a p-value, I'm not going to ask for a p-value in the questions of 9.3, because p-values 9.3 using a t distribution are a little bit messy in some ways. Of course, you could use the calculator and it would be less messy, but this is doing, they're giving us the critical value tables for the t distribution table to get these p-values, and it's just a little bit messier. So I'm just gonna, I need to ask a question from 9.3 and also 9.2, but 9.3 I won't ask it from a p-value side. I would ask it from a critical value rather than a p-value. So I'd ask you to do a hypothesis test using the critical value method, not p-value. And let's just find some p-values using this, using the t-distribution table. And you'll see why it is a little bit messy. It's just because the t-value distribution table, when you're going for p-values, there's really not enough detail, so you have to have a span. Let me show you what I'm talking about. Let's take a look at this first one. And this first one shows that we want a p-value. Now, the p-value is actually, P stands for probability, and probability is the area under the curve. So if we take a look at the standard normal curve, and we're looking at a t-value, so the t-value is given to us. Sample size n is given to us. Now, so if the sample size is 19, we know that the degrees of freedom, which we need to use our t-table, is one less than the sample, so it's 18. And another thing that is going to be really important for us to look at is we need to know what type of test this is, And when you're, that's maybe not the best color, but the way you know if it's a left tail, right tail, or two tail is by looking at its alternate hypothesis. And when it says not equal to, that is going to be a two tail. That color's just not going to work, I don't think. So let's go two tail. And two tail just means that you've got both sides covered, because we don't, if it's not equal to it, not equal to whatever we're talking about, that means it can be above the mean. Remember, the mean is right here. It might be above the mean or it might be below the mean. So we need to find p-values, or with using critical value method, critical values that are above and below. So that's why it makes two tails on the left and right. So, so what we need to do is we need to look up, so they gave us a negative 1.445. Now we also know that this is symmetric, and so this point right here would be a positive 1.445. And something that's really important for you to notice when you're dealing with, this would be your p-value, but oh, I take that back. Your p-value is going to be, the area under, since it's two-tailed, your p-value is going to have to be the area under both tails. But when we look this up on our chart, it's going to be first with one tail, and then you just double it. Now, the reason why I'm focusing in on this right tail, now remember with z-scores, it's easier to find area on the left, and it's easier to find the area on the left with z-scores because the table is set up finding area right on the left of your z-score, right? That's how z-score tables are set up. There's a z, and there's a z, and there's given us area to the left. But a t table is set up giving us, here's the t, and the table gives us area in the right tail to the right, okay? So you got to be aware of that. So that makes it easier for me to find right-tailed areas. And so let's go back to the information we're going to need to do this. I wish I had this closer. I didn't have to mouse around with this thing so far. But the critical pieces that we need is we're going to need to know this critical value, or this t value, I should say, 1.445, and I also need to know the degrees of freedom of 18, and I also need to know, that's it, that's all I need to know. So let's go find that. There's z, and let's go t. All right, we said the degrees of freedom are 18, so that's going to be right along there. 18. And we're looking for a value of 1.445. So notice I've got 1.3 right here, 1.33, and then I've got 1.7. I want 1.4. So that here's the problem that I'm talking about, is that I'm looking for 1.44, which is right in between, maybe not even exactly in between, but it's in between those two. So when I look up area to the right, I get these two different areas. And I know my answer that the actual area that I'm looking for is in between those two areas. So this is why there's not as much detail with this, right? Because we're just given areas right here, and there's not that many different area outcomes on the area to the right. So there's not a lot of detail. So you end up finding yourself in between the two areas. Now, as the t number goes to the right, the t value gets bigger. But you know, when you take a look at this, as you go to the right, as you go to the right, the area gets smaller. So that's why if I say, okay, I'm looking for a p-value that's, right here, well, it's going to be between these two p-values, these two areas. And you're going to put this one first because that's the smaller area, and then this one's the larger, right? That's the smaller. So 0.05 to 0.10. That was too far. So that would be point 0.05 to 0.10. Now the thing is, there's two of those, right? So it's doubled. So I need to say 2 times 0.005. And when I double that, I get basically 0.10. And then this one was 2 times 0.10. And that gives me 0.20 or 0.2. Once again, the reason why I'm doubling it is because it's a two-tailed test, and two-tailed test has 2 equal areas on both sides, so it has to be doubled to get the full p-value. All right, let's do the next one. Hopefully this will go a little bit quicker. Now, once again, we're going to need to look at this and figure out what kind of test is this. And so, once again, I love pictures. I do my quick picture, my standard normal. Here's my mean right in the middle. We're trying to figure out if the mean is less than this number. Well, if we want to know if it's less than, we want to know if we want to know if the mean is less than some number, right? That's going to be to the left. Less than is to the left. So the alternate hypothesis says the mean is less than some number. Well, that's going to be a left-tailed test. Okay, so remember, once again, our p-value, it's just, now this is just a left-tailed test. So there's only one tail, so you don't have to double anything. It's just right there. So that's what I want. I want that p-value. Okay, that's what I'm looking for. Now remember, I told you that the t-distribution table is really better set up for finding areas on the right. Now, what I'm looking for here is, you can see my t-value is right there. It's negative 3.164, but I don't have area to the left. Now I could subtract from 1 and do that whole thing, but in my mind it's just easier just to find this exact area. Of course, this is on the opposite side, but because of symmetry, not cemetery, because of symmetry, this 3.16 positive 3.164 is going to give me the same. It's going to give me the same area, which is the p-value. Okay, let's look it up. What do we need? We need a degree of freedom, which is 1 less than the sample. Degree of freedom is 10. And we have our t-value we're looking up. Our t-value is 3.164. Degree of freedom, once again, is 10. Okay, we should be able to do this. Get down there. Maybe I clean this up a little bit here. Start over again. All right. What did I say? Degree of freedom is 10. Oops. Degree of freedom is 10. We're looking for a t-value of 3.164. So as I'm going along here, 3.169. Wow. I mean, gosh, it's so close to that. I'd be tempted just to use that. But they're asking us what is it in between. So 3.164 is barely smaller than this, but bigger than this. So it's going to be in between. It's going to be in between these two guys. Okay, so we would say that the p-value is going to be bigger than 0.005. That's really sloppy. We're going to say this p-value is in between 0.005 and the p-value is going to be, so it's going to be bigger than 0.005 and less than 0.01. Okay, and that's going to actually be our answer. So let me go ahead and put it in the answer column up here. And here it is right here, and the answer is 0.005 So P is greater than 0.005 and less than 0.01. All right, let's look at the next one. So this is a little bit redundant, but it kind of gets you into figuring out p-values, because that's something that's important for doing hypothesis testing. And then the next round of 4 questions will be critical values, and then we actually do a hypothesis test. So let's get our picture. There's your mean. My alternate says it's not equal. Okay, that means my test is going to have to be a two-tailed test. And like I said before, it's going to be easier to find the value over here to the right because that's how t-distributions are set up. Some bits of information is that our degree of freedom, degrees of freedom is 26. Also important is there's my t-value, which is 1.752. Another area of mistake is, remember with two tails, you would have to actually add those two areas up, which is just basically doubling this area, right? Because the areas are equal. So just double. So I'm trying to find this p-value right here. And then I just double it since I've got two tails that are same size. Okay, so what do I have? I've got, just to review, degrees of freedom 26, a t-value of 1.752. All right. Degrees of freedom of 26, so right here. I'm looking for 1.752. There's 1.7, not 5, so it's going to be a little bigger than that. So this is 1.70 and I need 1.75. So that's the smaller side, and then there's the bigger side right there. So it's somewhere in between these two areas. So this is I'm going to call this alpha because remember there's two tails, so I'd have to double to make it a p-value. So alpha is bigger than 0.025 and alpha is less than 0.05. Okay, 0.025 and 0.05. So now remember there's two tails, so let's be careful. This is an easy place to screw this problem up right here. I mean, really, you got really good understanding if you've gotten to this point, but you still can mess it up. Because, what did I say that was? This is 0.025. And this was 0.05. But the thing is, that's just this area right here. So we're saying the p-value, this area in black on the right is somewhere in between these two p-values, okay? But we've got two of them, so we're going to have to double it. So let me do that over here. I've got to double this 0.025. And so 0.025 times 2 is 0.05. And the other value was, what, 0.05? So I got to double that. And when I double that, I get 0.10 or 0.1. 0.1 or 0.10, whatever, however you want to write that. And one more to do, p-value wise. Do a quick picture. There's the mean, we're saying, and the alternate hypothesis, mean is greater than. Well, to test if something's greater than, you have to do a right-tailed test. Since there's only one tail now, I don't have to worry about doubling. I could just say that this is the p-value. And yeah, there, I'm going to fix that right now. Now that I remembered, this is not actually p-value, that's alpha, and then double it, now you get the p-value. This is just one tail, so we're off to the races right away. The important piece is our degrees of freedom is going to be 6. Our t-value is right here, and it is 1.847. That's the t-value we need to look up. Degree of freedom is 6, right? Yes. Okay, so it said the degrees of freedom is 6, so let's circle that. I'm looking for a t-value of 1.847. Okay, so there's 1.4 and there's 1.9. So 1.84, so the t-value I'm looking up is 1.847. Unfortunately, this table doesn't have that, just like all these other ones. It's somewhere in between. So we're looking at something in between those two. So the p-value that we're talking about, or if I go with this picture, we'd say that the p-value is larger than 0.05 and smaller than 0.010 or 0.01. 0.1 rather, not 0.01, 0.1. Okay, let's put those answers in. And so if I get back there as fast as I can. There it is. So 0.05 and 0.1 or 0.10. Okay, so now we're still practicing hypothesis testing, not actually getting into hypothesis testing. Remember, there's two methods of doing hypothesis testing. One is using p-values, and we spent time on 4 different examples of how to find p-values. And remember, the p-value is the probability or the area under the curve. Very, very important to realize that. And then when you're finding critical values are actually the t-scores or t-values. Those are the critical values. Okay, so those are the two different, I mean, they're very similar in a lot of ways, and they are applied to similar kind of problems. It's just that they're two different ways of getting the same outcome. I'm going to go ahead and go back to drawing my pictures again. On this first one, I take a look at my alternate hypothesis. It says greater than, so to do a test, it's going to have to be a right-tailed test. Now, this is different. This is, I want to know the critical value here that sets us apart from whether we accept it or reject. And that's what the p-value did also. But the p-value, you're actually looking at area, so you always want the area. The p-value, if the p-value is smaller than your significant level, then you reject because you're further away from the mean. In this case, we're not looking at areas, we're looking at t-values. So this would be the divider from where we do not reject, or over here, if you land over here, you reject. Okay, and we'll get into that when we actually do a problem. But first, we got to figure out what that critical value is. How do you do that? Well, actually, it's easier than the p-values, at least using the table. You need to know that alpha, that this area is 0.01. And we also need to know degrees of freedom, and that would be 1 less than the sample size, so 19. So what is the t-value right here? Well, we can look it up. New problem. What do I need? I need alpha is 0.01. That's the area to the right. And I need to know degrees of freedom is 19. Let's go to our chart. I should have put this closer, this table, so I don't have to go so far. But that's too late now. Let's see. Oh, that's not getting cleaned up. Okay, let's go back here. We said we have degrees of freedom in this problem. Happens to be 19. Right there. And we also know, look at this, area to the right, area in right tail. Well, we already know that. That area of the right tail is 0.01, was given to us. That's the alpha. That's the alpha, 0.01. So what t-value goes with that? Well, it's actually very accurate, unlike going the other way. This way is really accurate, and I see that my t-value is 2.539. And that's the critical value. 2.539. That's what we just found right there. This critical value from don't reject to do reject tells us if you cross this point, you're going to reject if you cross the point to the right. So this is t equals 2.539. All right, let's do it again. This does go a little bit quicker. You don't have to draw a picture every single time, but you know, since I'm a teacher, there's your mean. Alternate hypothesis says the mean is less than, so that would be less than the mean. Less than would be a left-tailed. We have a significance level where alpha is 0.1 or 0.10, and we've got our sample size 22, so degrees of freedom must be 21. All right, let's look it up. Okay, so we said the degrees of freedom happen to be 21. We also said that the alpha, oh, wait, which one is this? What number are we on here? Okay, let's see. I need to go back real quick and take a quick peek at something. Oh, yeah. Okay, let's take a quick peek. This problem is a left-tailed, and if we were talking about z-scores, that would be awesome because z-table always gives us area to the left. But I want to know what that t-value is, and since I'm to the left of mean, which is 0, you know that's going to be a negative. But my t-values are not. My t-table is not set up that way. My t-table is set up for finding area to the right. So it's just going to be, you could always subtract by 1 and do other ways, but for me, it's just easier just to look up this guy here because it gives me, because I know of symmetry that this green area is equal to this black area. So I know, and how do I know? I mean, look at, I'm gonna make it the same area, just 0.1 or 0.10, right? And so if I look up this area with this degree of freedom, it's going to give me a positive number, which will be the same as its opposite over here. So that's how I like to do it. Okay, and then I'll just put a negative on it, and I got it. Let's look it up. Okay, so we said degrees of freedom is 21. We said that the area is 0.10 right there. Should be easy enough to look up. And notice it's a positive value because we're right here on the right hand side of 0, right there. So that t-value is 1.323. 1.323. Just using the colors again. 1.323. But we know that it's the left of 0, so this, what we're looking for is the negative, the opposite of that, so negative 1.323. So this critical value, or t-value, is negative 1.323. Okay, let's do it again with another problem. We have not equal to it in the alternate hypothesis, so you know that that must be 2 tails. Okay, so we got 2 tails to deal with. It's going to be easier to find this alpha. Oh, sorry, we are going in the other direction, right? We're going the other direction. We are given that this area has an alpha of 0.01. I want to find that critical value there. And once I find that, no problem. This is just going to be the same number except opposite. So when we write our answer and we're going to say plus or minus, there's going to be 2 values here. Now when we take a look at, let's see, the sample size, we know that the degrees of freedom are going to be 1 less than that, so that's going to be 6. Let's look it up. We got everything we need, right? We got the alpha, area to the right tail, and we've got our degrees of freedom. Okay. So let's see, degrees of freedom 6. Oops. Degrees of freedom 6. Oh, I'm about ready to mess up, aren't I? This gives us area to the right, area in the right tail, right? This gives us area in the right tail. And what is the area in the right tail? Yeah, I almost messed that up. See how easy it is? I didn't mess it up. I caught myself. So remember your alpha. So with the difference on this problem is that we have two tail. Got to be careful with two tail. So all together, when you put those two tails together, you're going to have your alpha, which is 0.01. Okay, you're going to have alpha 0.01. Now what we want, because we're looking this up, we want half alpha, right? Because we're just looking up this part right here, this little right tail. So that's half of alpha. So if alpha is 0.01, half of alpha is 0.005. That's what I got to look up. Whew, almost messed that up. Okay, so I go ahead and take a look at degrees of freedom 6. Degrees of freedom 6, and looking up with an area to the right tail, 0.005. There's 0.005. Where do these come together? Right there. So we're talking a t-value of 3.707. So we're talking about a t-value right here is 3.707, and this is negative 3.707. So there we go, plus or minus 3.707. Okay, last one of these, and then we have a hypothesis test to do. Once again, it's not equal, so therefore we're talking two tails. And we just did one, so make sure we don't mess it up or get close to mess up. I didn't quite mess it up, but I kind of was getting close to messing that up. Let's see, let's make those, try to make those equal. Those two tails, that's just a bad drawing. But we're going to go with it. So we know that alpha is 0.05. So if I just want to, oh man, this thing just went to eraser. If I want to take a look at just the right tail, because that's how t-distribution works, the t-table works rather, then I'm going to take half of alpha. So if I take 0.05 and cut that in half, that gives me the number I'm really trying to find in the right tail, which is an area of 0.025. That's what I got to look up for just this right side. Okay, degrees of freedom is going to be one less than the sample size. Degree of freedom is 27. I'm looking up an area of 0.025 right here. Haven't used brown in a long time. Okay, so degrees of freedom is 27 right here. And area in the right tail is 0.025. 0.025, this guy right here. Let's get on down here to this intersection point, and we're talking t-value is 2.052. 2.052. So critical value is 2.052, and the other one is negative 2.052. So the answer is plus or minus 2.052. Okay, here we are. Last problem, number 3, question number 3. It is asking us to do a full-blown hypothesis test. Now, I'll tell you the labeling your variables is going to be really important. And most probably important is distinguishing the difference between a sigma, which is population standard deviation, and little s, which is sample standard deviation. Okay, those two things are really important because if sigma is known, then you're going to use your z test statistic, and you can see that in the. Let me just go to that. Once again, if your population standard deviation is known, sigma right here, then you're going to use the z. You're going to use z. But if your population standard deviation is unknown, you're going to use your S, which means t statistic, t distribution for your test statistic. Okay, so when you're reading a word problem, it's super important that you're able to get through and figure out what's sample and what's not sample, what is population and what's sample information. Usually what happens is they will say a sample, and then after that, they're talking about sample data. But let's see. A market research firm reported that the mean annual earnings of all family practitioners in the United States, so there's their mean earnings of doctors, I guess, family practitioners. So mean, they're talking about population mean, which is $178,258. That's not a bad income. And then notice where it changes its language. It says a random sample of 47. Okay, now we're talking about a sample. I'm going to do this in red. 47 is the sample size. Oh, by the way, that means degrees of freedom is going to have to be, what, 46? So a random sample of 47 practitioners in Los Angeles had a mean earning of, now we're talking mean of the population. Well, we use X bar for that, and they helped us out. They did the same with notation. So they did a random sample of 47 family practitioners, and they had a larger mean, at least in the sample, $192,890. $192,890. That's just a little more than I make. Yeah, a lot more. So anyways, so that's the. So what are these sounds my phones are making? My phone, I don't remember ever making that sound before. But anyhow, I'm getting a little distracted. It says the sample mean is right here. And then it follows with a standard deviation. Now this is where students go a little bit crazy. Is that population or is that sample standard deviation? Well, they're talking about a sample. So once they refer to a sample, then they, in general, right after that, all this information is just all stuff from the sample. So don't call that a sigma. That's not population standard. That is a little s. That is a sample standard deviation of $43,117. All right, well, we don't have a sigma. We have an S, which means we're going to be using the t distribution or t statistic, right? We can look that up again, but I think I just showed that to you on the formula sheet. What else do we need? Do the data provide, that sounds funny. Does the data provide sufficient evidence to conclude that the mean salary for family practitioners in Los Angeles is greater than the national average? Use alpha significance level of 0.01. Okay. So our null hypothesis, so our assumption is from these, the report from the practitioner is our population mean, which is $178,000 and $178,258. Okay, now the question here is, does the data provide sufficient evidence to conclude that the mean salary practitioner in Los Angeles is greater than? There's the number, or there's the word that I got to really focus in on. So our test, darn, this thing keeps on switching on me to eraser. But our test is the mean actually greater than this population mean of the whole country? Is the mean greater in Los Angeles? Now remember, they randomly sampled 47 family practitioners in Los Angeles. Now notice that this is a greater than symbol, which means what kind of test is it? Well, once again, we could do a quick visual. There's the mean. And if I want to see if something is greater than the mean, that's got to be a right-tailed test. And you know, really, if I'm going to show this accurately, you know, its significance level is 0.01. I mean, really, 0.05 is unusual. So 0.01 is this tiny little bit. So if we actually end up in this little region, oh man, we definitely got to reject, because to get down there is not very common. 0.01 is the area there. So let's see, what way did they want us to do this? Use the alpha of 0.01 level of significance and a critical value method using the table. Okay, we need to find a critical value. So that means that this little alpha here is 0.01, right? Okay. This is a right-tailed test. All right, okay. Next part of the problem, find the critical value. Round your answer to 3 decimal places, okay. Fine, so we just found a bunch of critical values. We just found 4 of them. So we could find this quickly now. What do we need for this? Well, we need an alpha level, a significance level of 0.01. And what is our degrees of freedom? Degrees of freedom is 46. Okay. So let's go figure this out. Which section am I on right now? Number 1, no, I'm on number 2. Yeah, right here. So go back to make sure I have all my information. Degrees of freedom is 46. Alpha level is 0.01. Okay, let's look it up. Orange. Haven't used orange ever, I don't think. So degrees of freedom is 46. This brings up a little thing here. So let me write degrees of freedom is 46. So the rule is if the degrees of freedom are not on our chart, then you drop down to, and we're talking about if your degrees of freedom are less than 200 and it's not on the chart, then you drop down to the next level. So even though 46 is closer to 50, we drop down to 40. That's more conservative to drop down rather than, if we go up to 50, that's saying that we had 51 in our sample. That'd be lying. So it's better to drop down, more conservative, I should say. So we drop down to 40 as the degrees of freedom, because 46 isn't on here. And since I'm down here, I might as well say this again. I know I did before. But if you have a sample size bigger than 201, right, then we just use z-scores, right? The t-distribution table just turns into a z-table. And that is because when our sample size gets extremely large, bigger than 200, then our t-distribution pretty much approximates as very, very close to a z-distribution. And so we just use that, okay? All right, I know I said that before, but anyhow, that can, just to kind of put things together, I guess. It might not even be that useful, but anyhow. Our degrees of freedom, here we are at 40. And I forgot area to the right is 0.01. Area to the right is 0.01 right here. Ooh, it's doing something weird. There we go. 0.01. So then I go all the way down here and look where that intersection point is. And I get a t-value of 2.423. 2.423. Okay, let's go up. we just found out that our critical value is right here at 2.423. What does that mean? Well, that means if my test statistic, now remember what that is. Test statistic comes from my sample size, or my sample mean, right? Comes from the sample mean, and so that comes from my sample. So if I plot my test statistic, which is going to be a t-value, and it lands somewhere in this region, I am not, so do not reject, right? And that just is basically saying, like I said, I think, last time we talked about this. Yeah, I go out, I've got this population mean. I want to see if doctors make, more than the mean of the population mean, to make more than that. Doctors, according to that census, make $178,258. Well, we sampled 47 randomly in LA, and we want to know, do they make more? Now, if we plot that sample mean and it's somewhere in here, we can say, given this significance level, we could hit these points by chance, just by sampling. All those plastic surgeon doctors, they make way more than that. But these are family practitioners. So anyhow, just by chance, it can be somewhere in here. So we're not going to reject that because it can be there by chance. But if we are in this highly unlikely point, 1% way out here, if we plot our t-value and it ends up over here, we are going to definitely reject that because that is so unlikely for it to be there. We're going to have to reject. I don't think, we don't feel like that's by chance to get way out there. That's so unlikely. We are expecting, right? We are expecting it to be somewhere in here, somewhere, if it's greater than by chance, and so the further we go away from the mean, plotting our values, the more we say, I can't, how could that be the mean? If this is actually the mean, then we should be close to that mean. But if it's way out of here, no way. And then that's why we reject. Okay, that's our game plan. Next, compute the value of the test statistic. Well, where do we get that from? Well, we have a formula. And maybe I should get rid of all this stuff. It's kind of sloppy here. Let's get rid of all this stuff. And you can see that because we have the sample standard deviation and we do not have the population, it's unknown, population standard deviation is unknown, we're going to use the test statistic with a t. So we use this formula to plot our t-value and to see if we're going to reject or not. Let me write that again just to kind of remember, or for everybody to see the formula. And the formula is going to be our sample mean minus the population mean. And they have this little sub-zero notation just to show you that that's the population mean that is in our null hypothesis. That's why they put the little null or not or zero sub-notation there. And it's divided by our sample standard deviation divided by the square root of n. Okay, let's do this. So sample is 192,890 minus population mean 178,258. That gets divided by sample standard deviation 43,117, which gets divided by square root of sample size 47. And up top, we do the subtraction and we get 14,632. And we do the division of the square root of 47 and we get approximately 6,289. 6,289 point, and I try to have as much value. You definitely do not run around in the middle of your work. You can around at the end. Daughter's calling. Okay. That's probably not important, right? Your daughter calls. Anyways, 260838. So basically, you just leave that in the calculator. You don't want to round because you'll really change the value of this. So 2.326505511. I'm a little distracted from the phone call. 2.326 let's see, 650 5511. I think that's enough detail now. Okay, at that point, it says round to 3 decimal places. So now we round down, or round to 3 decimal places. So this is going to be 2, approximately, the t-value is 2.327. Yeah. Okay, well, this is the moment of truth. We're going to plot our t-value of 2.327 and see if we reject or not. And when I go to plot my test statistic, what was that number again? It's 2.3, 2.3, about 27. That's from my data, right? From my sample. Well, that's definitely smaller than 0.4, right? 2.3 is smaller than 2.4. So it plots to the left somewhere, you know, I don't know exactly where, but it's definitely to the left. Oh boy. Uh-oh. What did I just... There. So it's definitely going to be to the left. So somewhere over here, which means you're in the do not reject region. So we go over here and it says determine whether to reject. No. Do not. If this pen will work, do not reject. Do not reject the null. So whenever you reject the null, then you can make a nice strong statement. Whenever you do not reject the null, your statement is wishy-washy. And the statement is there is not enough evidence to conclude that the mean salary for family practitioners in Los Angeles is greater than the national average. There's not enough information. The only way we get enough information is if we did a sample, we did a test statistic, and that darn thing was in this rejection region, meaning it was, you know, it got us into this 0.01, smaller than 0.01. Well, at that point we reject, and then we can say a lot. We can say that the average practitioner salaries in Los Angeles would be greater than the national average. Because our test statistic was less than, it's in this non-reject region, it just gives us really not strong conclusion. But there it is. I hope that helped out, and that was a little bit long, but there it is for you. You could always fast forward me and put me on double speed talk or whatever. And so that probably is helpful, or slow down and listen to it again. Okay, I hope everybody's doing great, and take care.